This is lecture 4, Rational Expectations and New Keynesian Economics. In lecture 3, we learned about policy and effectiveness. We also realized that the problem for the proposition of policy ineffectiveness, i.e. that you leave the economy to its own devices, there is no place for monetary or fiscal policy. This proposition does not fit well with what we see reflected in the data, something we call the stylized fact. So the proponents of ineffectiveness have this issue to address. The traditional Keynesian proposition is that economic activity can be manipulated by aggregate demand. So the economy is demand-led, which in effect gives us room for economic policy. If policy can drive aggregate demand, then aggregate demand does the job of driving output. But this proposition was destroyed by the rational expectations result. Here we have the solution for output, RE solution for equilibrium output, YT is equal to gamma over 1 plus gamma mu T. The equilibrium output is just a proportion of the economic shock. Notice the absence of money supply in this solution for output, telling us that there is a policy neutrality implication. So with these models being micro-founded, having expectations and policy neutrality, there had to be a Keynesian reaction to this, because the traditional Keynesian proposition had been destroyed. So in comes the new Keynesians, who are going to put an answer to this, still using models that are micro-founded, but can cope with persistence or persistent movements in output away from the long run. The models that New Keynesians came up with were similar to the rational expectations models in the way that they were micro-founded and included rational expectations, but were different in that they were stylized to reduce the adjustment of prices or wages. So in other words, the Keynesians were like a bolt-on, if you like, the standard, the new models, one of sticky prices, or something we call price inertia. And these innovations to the models were called nominal rigidities. There is a rigid nominal variable, and that allows us to have movements in output. When we fix prices, it's output that has to move from movements in aggregate demand, and that's what they did. So two commonly used nominal rigidity models are that of John Taylor and Guillermo Cowbo. In the Taylor contracts, firms have fixed periods when they can change their prices. So this is actually specified within the model that prices can only change so often, and that's how we get price stickiness. In the Cowbo contracts, firms wait to receive a signal. When they receive the signal, they can change the price. When they change the price, they change it to the price they want to achieve, given the economic conditions now and also the expected economic conditions in the future. So it's a slightly more elaborate price setting mechanism. And we're going to use Cowbo contracts in this course rather than Taylor contracts. And we're going to take the Cowbo contract and derive from that the new Keynesian Phillips curve, which is a key equation in the DSGE models, but more importantly, it's an equation that tells us about the evolution of inflation, and so it tells us also about the evolution of prices. So the Cowbo contract, which is equation 1, assumes that there are n representative firms, and each firm, and the firm is denoted here by I, will set its price bearing in mind that it wants to minimize this quadratic loss function. And the loss, as given by equation 1, is half the expected future discounted value of the difference between the price of firm I in the future, t plus j, minus the target price for the firm. So whilst the firm's price is away from the target price, as it would like to say, then we can say the firm is making a loss. Now we know that the firm can only adjust its price if it receives this signal. So whilst it does not receive the signal, it's making a loss. And the probability of not receiving the signal is omega. That's why we add omega to our loss function, so that we can rewrite the Cowbo contract as half the expected future discounted stream. So these are the expected losses. First of all, multiplied by the probability of not receiving or not being able to adjust the price, times a discount factor multiplied by the difference between the firm's price and the price it would like to set, the target price squared. Now the Cowbo contract allows for the fact there is a probability of making the loss, so that has to be in the loss function. So if the probability of not receiving the signal is a half, 50%, then we have to assume that the expected value of the loss will be multiplied by 50% also, half the chance of actually realizing the loss. Now, to derive the price that firm would like to set, so his price choice, what price will the firm I choose if it receives the signal? Then we can minimize the loss function with respect to PIT. And when we maximize or minimize anything with respect to something, what we are with respect to is the decision. So here the decision is for the ith firm and the price they would choose when they receive the signal. So we effectively are minimizing with respect to PIT the price of firm I at time t of half the expected future discounted weighted for the probability difference between the firm's price and the target price. Remember, so long as the firm does not receive the signal, the price that it has remains the same because it cannot change it. So it continues to make a loss so long as it does not receive the signal. When it receives the signal, the firm chooses the reset price. Now, if we differentiate with respect to PIT, we use the chain rule to minimize the Cowbo contract. We have the expected future stream, future discounted stream of the difference between PIT plus J minus P star T plus J. Effectively, the 2 has come down, we differentiate, which cancels out the half, and we're left with 2 minus 1 as a power, which is just to the power of 1. So here we have our first order condition the minimization with respect to PIT on the left and 0 on the right hand side, which means it's a first order condition where the slope is equal to 0 is where the firm chooses its price. Now we can split the first order condition. Here is the first order condition. We're going to split this into two parts. This part here and this part multiplied by omega beta over stream. So we split this bracket into two. We have first term is PIT, which comes from here, times the summation of omega to the j beta to the j, minus the summation of omega to the j beta to the j times the expected value of the target price P star T plus j. You might be wondering why PIT is outside the summation side. Well, it's a common factor because we know that if the firm is not changing its price, then all future prices are the same. PIT is equal to PIT plus 1 is equal to PIT plus 2. So they're a common factor. We can bring them outside the summation sign. And also we know that the expected value of a choice variable is equal to itself. It's already realized. It's now exogenous. It's taken part of this decision. It's realized from this decision. So the expected value of PIT is just PIT. And with these two terms, now we can put one on the right hand side and we can rearrange this equation to give us an expression for the firm's reset price. And here the reset price is XT. So we've replaced PIT in the line above with XT to denote that it's the optimal price that firms would choose at time T, given their ability to do so and bearing in mind the future costs for the firm. So we can rewrite the first order condition now to give us the reset price XT, which comes from here, is equal to 1 minus omega beta, which comes from this part here, multiplied by the summation of omega beta EP star to the T plus J. So there is the reset price for the firm. We should do well to remember that. Now we can take the reset price from the previous slide and rearrange it, just as we did in lecture 1, into a simple dynamic equation. So here we have a variable xt that's expressed as a future j discounted beta stream with another variable which happens to be p star this time. And in lecture 1, remember this example was pi t on the left here and marginal cost mc on the right here. Doing the same manipulation to achieve an equation that's dynamic in xt. Xt is equal to some proportion of xt plus 1. There is the relationship over time of xt, so we're injecting some dynamics. Just as in lecture 1, we take the case of j is equal to 0 out from the stream. You can ignore this line if you want. Just got a line through that. It's just a different way of doing it. We can take, as we did in lecture 1, the case of j is equal to 0 outside the stream. And this is the term here. We set every term in this equation, set j is equal to 0 here. For the one case, we will find that this is equal to 1 minus omega beta times p star t. And as we've taken the case of j equal to 0 out, we have the rest of the stream here, so we can add the rest of the stream, but the stream is now from j is equal to 1. So basically written out the progression in terms of the first case, which is j equal to 0, and in terms of the remainder of all the other cases, which is the summation from j is equal to 1 to infinity. Now what we can do, just as we did in lecture 1, is multiply this second term on the right hand side by omega beta and divide it by omega beta at the same time. And if you look at the maths in lecture 1, you'll see how we can, when we do that, we have a line or denominator here with omega beta underneath, which would have given us omega to the j, beta to the j minus 1, omega to the j minus 1, beta to the j minus 1, which we can then roll back to j equal to 0, but we have to add 1 to all the subscripts. So there's a couple of steps missing from this line to this line, but that's given in lecture 1 when we derive the simple dynamic equation. But this omega beta comes from the requirement to manipulate these j's here. Notice now, with it manipulated in this way, that this part of the second term on the right hand side is actually equal to the expected xt at time t plus 1. So rolling this one period forward and taking expectations, we will have this term here, which we can now write as omega beta times et xt plus 1. So if we take the expectation of xt, we will have this. So we've replaced this with ext plus 1, because that's what it is. Now we have the dynamic equation xt is equal to 1 minus omega beta p star t plus omega beta ext plus 1. Now that we have found the reset price for the firm, and we have represented the reset price in terms of its dynamics, xt and xt plus 1, we can now discuss a little bit more about the target price, P star t. Well, P star t is going to depend on variables, and the most obvious can be the aggregate price level. So the prices are going up in general. This is going to put upward pressure on the firm's target price. Obviously, economic activity will have an effect on the target price. So if the economy is growing faster than its natural rate, something that we say, well, there is a positive output gap, there's excess, there's heat in the economy, that's going to be driving up the target price as well if firms are busy. And of course, there can be all kinds of price shocks for a firm. So for instance, there might be an increase in the price of oil. That's going to have an upward effect on the target price. So that we can write the target price, P star t, as dependent on the overall price level, the output gap, and the price shock. And we can substitute for PT star into our dynamic reset price to get that the reset price xt is equal to 1 minus omega beta times P star t, which now we are replacing on the right hand side of equation 5, and omega beta times the expected reset price in the future. Notice that if we expect prices to increase, or if the firm expected reset price increases, this drives up the reset price as well. So we are now halfway through deriving the new Keynesian Phillips curve, and we can use this key equation with the aggregate price mechanism, which we're about to see, and derive the supply equation, or something called the new Keynesian Phillips curve. So what is the aggregate price mechanism? Well, we can look at how prices are dispersed in the economy, how price is made up at an aggregate level, and we can say, well, the overall price level is going to be 1 minus omega, so that's the times the reset prices. So this, remember, 1 minus omega is the probability of getting a signal. If firms got a signal, then they were able to change their price to the reset price. But there was also a portion of firms in the economy that were unable to change their price, so price is at its previous value times the probability of not receiving the signal. This becomes the aggregate price mechanism. And we can manipulate this mechanism and then substitute out xt. First of all, we take expectations and update by one period so that t becomes t plus 1 and pt becomes ept plus 1. This is just a constant, 1 minus omega, and then we have ext plus 1, and omega is also a constant, and the expectation of pt minus 1 is pt minus 1, but updated one period, just pt. So if it's already happened, the expectation of that variable is itself. Now we can rewrite this equation 8 with this first term on the right hand side on the left. So in terms of the expected future reset price, 1 minus omega ext plus 1 is equal to ept plus 1 minus omega pt. Remember, we're working with the aggregate price mechanism. Now we're going to introduce inflation, and we do that by subtracting and adding pt to equation 9. So here is equation 9. Notice that we've taken pt away and added it, so we've done nothing overall, as these two terms cancel out. And we can rewrite this right hand side as ept plus 1 minus pt, which is from here, and two other pt's, 1 minus omega pt, 1 minus omega pt. Now, pt plus 1 minus pt is inflation in t plus 1, so the expected value of p in t plus 1 minus pt must be the expected value of inflation by t, in other words, by t plus 1. So we can replace this term in equation 9 with expected future inflation here. We have equation 10 in terms of the expected future reset price and expected future inflation. Divide that through by 1 minus omega because it was on the left and we want to solve for ext plus 1. And we have equation 11. ext plus 1 is equal to 1 over 1 minus omega multiplied by the expected future inflation plus 1 minus omega times pt. And we can substitute equation 11 into the firm's optimized reset price. Remember that the firm's optimal reset price was written in terms of dynamics for xt, with xt on the left and ext plus 1 on the right. So we're going to replace ext plus 1 with the right hand side of equation 11. So the firm's optimal reset price, xt, was 1 minus omega beta times p star t, which we replaced, plus omega beta times ext plus 1. We know from equation 11 that ext plus 1 is actually equal to 1 over 1 minus omega, which comes from here, times expected future inflation plus 1 minus omega pt. Now, we have an equation for xt where e of xt has been substituted out. Now we're going to go back to the original aggregate price mechanism and substitute out xt altogether, now that we have future inflation already inside xt. Remember that the aggregate price mechanism was that pt is equal to 1 minus omega xt. It's this proportion of firms in the economy 1 minus omega times the reset price, and the remaining portion of firms with their prices stuck in the previous period. So we're going to substitute out xt by putting all of this, slotting that into this xt inside the aggregate price mechanism. So using this aggregate price mechanism and replacing xt with what we had earlier, we have PT is equal to 1 minus omega times xt. But remember, xt now is equal to this term, which includes everything here before the last part of the aggregate price mechanism, which is omega pt minus 1. So it was 1 minus omega times xt plus omega pt minus 1, but now it's this long term here. Notice we have everything in inflation in terms of prices and real activity yt. We can gather all the p's on the left hand side, and we have this term here, 1 pt minus 1 minus omega 1 minus omega beta pt minus omega beta 1 minus omega beta omega pt minus omega pt minus 1 is equal to a lot of this that came from xt, a reset price earlier. To simplify the left hand side, we write out all these terms, we multiply out all these brackets, and see what cancels out. We have omega pt minus omega pt minus 1 is equal to this collection of terms on the right hand side, which is already starting to look like a Phillips curve. We have expected future inflation on the right hand side and some collection of constants multiplied by the output gap. Omega pt minus omega pt minus 1 is actually omega times inflation in the current period. Inflation is equal to pt minus 1. So we can rewrite the previous equation as omega pi t equal to 1 minus omega 1 minus omega beta times this, what remains of the target price for the firm, which is a function of pt alpha y tilde plus epsilon t plus omega beta times expected future inflation. So we now have something that very much looks like a New Keynesian Phillips curve. We can bring this to the left of the right hand side. So below we can write the New Keynesian Phillips curve divided through by omega. We have that pi t is equal to beta et pi t plus 1. So inflation is driven by discounted expected future inflation plus some collection of constants which are omega and beta. Omega, which was, remember, the probability of not being able to change price, which we can think of as the price stickiness parameter, and beta, the discount factor, times alpha, the amount the economy or the price level is affected by the output gap. So this collection of constants times the output gap plus the shock. And we can write this more nicely by replacing all these parameters with lambda. Okay, so we can say lambda is equal to 1 minus omega times 1 minus omega beta divided by omega times alpha. Similarly, zt is another collection which are around the shock. So we can rewrite the New Keynesian Phillips curve as inflation pi t is equal to beta times expected future inflation plus lambda y tilde t plus zt, which represents the economic shock. So let's look at this equation. What is the Phillips curve implying to us? That inflation is determined by expected inflation. In other words, our future prediction of inflation is feeding into inflation today. And that's a very interesting implication, that it's our opinion of the future that determines what happens today. Plus, there is obviously some measure of excess demand, which is given by lambda y tilde t. As we would expect excess demand or output to be much higher than its natural rate, that would feed through into inflation as firms become very busy and labour markets become tight. And also we would expect the economic shock or an economic price shock to drive up inflation. We still have this negative relation between inflation and unemployment. Remember that unemployment is negatively correlated, the unemployment gap is negatively correlated to the inflation gap. So we would write that as minus lambda u tilde t. So we still have this negative relationship between inflation and unemployment that we would expect. However, there's now this divine coincidence. If we write pi t, or bring expected pi t plus 1 to the left-hand side, if you write that out, you will see that it's possible for the central bank to achieve price stability and eliminate the output gap at the same time. Normally there is a trade-off between the two. And an influential paper that discusses this divine coincidence is the paper by Garley and Gertler from 1999, Real Wage Rigidities and the New Keynesian Model. If you want to learn more about the divine coincidence, I recommend that you read Garley Gertler, 1999, and Blanchard Garley, 2007. Just one digression from this was to help us to understand more about how inflation or expectations of inflation drive inflation. We can break the Phillips curve down into its sectoral, specific Phillips curves. So we could look at a particular market and say, well, obviously there's a Phillips curve for the aggregate economy, but we could also have a Phillips curve for each individual sector. So we said that inflation in sector K at time t is equal to the discounted expectation of future inflation in that sector, t plus 1, plus some collection of constants, 1 minus omega, the inflation stickiness in that sector, times 1 minus omega k beta, so the discount factor, this same collection of constants, only this time sector specific, multiplied by the output gap, which is the aggregate output gap, and some proportion of the sectoral output gap, so the difference between natural rate of output and actual output in that particular sector. So we could look at it in this way, and this was written in a paper by Alvarez and Burrill in 2010. Is a Cowbo price setting model consistent with micro price data? So in other words, Alvarez is suggesting that actually we could do better by having heterogeneity in the Phillips curve or in the model to explain the heterogeneity we see across sectors, so that we can try to give a more accurate description of the economy. But it helps us to look at something like the sector for corn as an example. We can see that the price of corn, if the sector was the corn sector, would be driven by the future expectation of the price of corn, plus the market fundamentals in the market for corn. So we understand that if there is excess demand or excess supply, this is going to have an effect on the price of corn, or the change in the price of corn. But now we understand more that it's also our predictions for the future price of corn that makes up the price of corn today. So the price of corn has two parts, that signal, the expected element, and the real part, which is given to us by the market fundamentals. So we see is excess demand in the aggregate level Phillips curve.